Okay, so you evaluated those first logs, and now we want to evaluate log base 2 of 6. And for those of you that are lucky and have the newest calculator's operating system, it has this built in. You can find it by either pushing the math button and going down to 0, or A, log base, or you can also find it in your alpha menus. So you know how you do the fraction by going alpha F1? Well, if you arrow over, it has some functions, and number 5 is log base. So if you choose that, it allows you to type in, I chose the wrong one. If you choose, it allows you to type in the 2, log base 2 of 6, and enter. 2.58. So wonderful if you have that, but if you don't have that, you feel like this is not fair because I can't type this in. So what are my options? Well, what we would do, 2.58, what we're going to learn that we can do is that we can let log base 2 of 6 equal x, because that's what we want to solve for. And if we take the definition of a logarithm and say this means an exponential form, my base is 2, my exponent is x, and my answer is 6. Now at this point, if you have a graphing calculator, you could also solve this by putting one equation into y1 and one equation into y2 and finding where they intersect. So this solves the problem for those of you that have a graphing calculator without the newest operating system. That being said, some of you have scientific calculators that don't have graphing options. So you still can't figure this out yet. But this leads into what we're going to do next and sort of develop towards. In 5.7 we do this a lot. And it's solving equations with logarithms. So if I have 2 to the x equals 6, you know with equations that what you do to one side of the equation, you do to the other side of the equation. And we're going to learn that if I have an equation with an exponent, if I take the log of one side of my equation, I can take the log of the other side of the equation, and they would still be equal. Does that seem true? That if 2 to the x is equal to 6, then log of 2 to the x would be equal to log of 6. But now we can use our log laws and say, I have a log law for exponents. What could I do with an exponent? I could bring it out in front and multiply. So part of our skills in learning how to expand was all leading towards questions like this, because now I can bring that x out in front, and I have x times log of 2 equals log of 6. And if I wanted to get x by itself, I would just have to divide by log of 2. So we go back to our calculator and check that out. If I would do log of 6 divided by log of 2, I get the exact same answer. So if you don't have a special base thing on your calculator, then this will work. You're welcome. Now the fascinating thing about our log laws is you can take the log. I took the common log of both sides, right? I could have chosen any base. I could have chosen log base 5 of both sides, log base 7 of both sides. I could have chosen log base e of both sides. Then there would be an e here and an e here and an e here and an e here. Now, why did I choose log base e? Because on all of our calculators you have a log button and you have a natural log button. So at this point, and I'm just going to redo it off to the side, if I started with 2 to the x equals 6 and I took log base e, which is the natural log of both sides. The natural log is the same as a log, has the same laws. So this exponent could come out in front just like it did last time. And if I wanted to get x by itself, I could divide both sides by the natural log of 2. And just as a way to check, we're going to go to our calculator. Instead of doing log 6 divided by log 2, I'm now going to go natural log of 6 divided by natural log of 2. What should happen? I should get the same answer. And I do. Now, because we could do this with any log, okay? Start a new page here. Let's say you want to find out what log 3 of 5 is, so you let log 3 of 5 equals x. You can always change that to exponential form. Okay, and just to really emphasize our point, let's go, Carter, pick the most underrepresented number between 50 and 70 that you feel occurs in mathematics. 57. Great number. So we could take the log of base 57. I'm going to write that 57 in green just to emphasize how underrepresented it is. Log base 57 on both sides. And I wrote that in green because you could have picked any number there. If I do that, I have a log law. This x could come out in front, and so I would get x log 57 of 3 equals log 57 of 5. And if I wanted to get the x by itself, I could divide both sides by log 57 of 3. Now, what did x originally equal? X originally was log 3 of 5. We let x equal log 3 of 5. So we can say log 3 of 5 is equal to log 57 of 5 divided by log 57 of 3. And this is a formula, or this itself is a specific example of a formula that's not on your formula sheet. I do have it up on the wall over there, called the change of base theorem. So on your next page, here it is, the change of base theorem. It says log b of x, and up on the board over there on the wall, I have log a of capital M is equal to log b of M over log b of A. It means we can take any log with any base, the base is A, and change it to a different base. That's why it's called the change of base theorem. The reason for it is what we just showed in our last example. So I'm going to go back one screen here for a second. We picked 57. It could be any number that we picked in green. And we changed the log base 3 of 5 to a new log with a new base, and it became log new base of 5 divided by log new base of 3. Now 57 actually isn't very helpful for us to choose, because typing that into our calculator is more like if you can type the little base 3, obviously the left is way simpler to type in than the right. But if you can't type in the base of 3, as many scientific calculators cannot, well, making the green number 10 is really useful, because now I can go to my calculator and I can just go log 5 divided by log 3. Or I could do natural log 5, because that's a different base, divided by natural log of 3. And all of these are going to be equal to log base 3 of 5. So it allows us to change our base, possibly to make it easier for our calculator to figure it out. And this isn't on your formula sheet because this process of letting something equal x and then taking the log of both sides and solving is a process that we're going to use a lot when solving equations. So you technically don't need it, but there are some questions that will do that being able to change a base quickly, multiple choice questions for example, will be very helpful. All right, question 1. Again, approximate each expression to the nearest thousandth. What they would do if this was a non-calculator question, they would ask, between which two integers would you find log 5 of 50? Right? And since you know 5 squared is 25 and 5 cubed is 125, log 5 of 50 would be between 2 and 3. Okay? This one's a little bit harder. Where would you find log 8 of 6? Well, 8 to the 1 is 8. 8 to the 0 is 1. So log 8 of 6 should be somewhere between 0 and 1. Okay? So now I'm going to use the change of base theorem and say this is equal to log 50 over log 5 so that I can type it into my calculator to see if I get an answer as I suspected between 2 and 3. Log 50 divided by log 5. Sure enough, 2.43. And just to mix things up for B, I'm going to write it as natural log of 6 divided by natural log of 8. My estimate was that it should be between 0 and 1. 0.86. Did it ask the thousandth? Great. Go back to my calculator. I need a 2 and a 1. There we go. Yes, it did say to the nearest thousandth. So we need to use our calculator. And the other thing that's nice about this is sometimes you can't find that log base even if you have it on your calculator. Sometimes you're searching for something on your calculator for a long time, not knowing where to find it. All right, questions for this one are 3, 4, and 5. We are going to do example 2 as well. No, we're going to let you do 3, 4, and 5 for a little bit, and then we'll do example 2.